Thanks for the opportunity to present in the 21st International Operation and Maintenance Conference in the Arabic countries. Today I will present the paper RAMS Program Methods Applied to Infrastructure's Physical Assets. My name is Dr. Eduardo Calixto from ECC, Germany. A brief introduction about ECC and me. My name is Dr. Eduardo Calixto. I'm a certified reliability professional, certified functional safety expert, certified automotive functional safety professional. I have 22 years experience in reliability safety engineering, has worked in projects for mining, oil and gas, rail and aerospace and defense industry in different countries across the globe. So you can see on the right side some clients that we currently have, in the middle some current and past partners. Here in the middle we also have the current partner that we have in the Middle East, and that are some companies that I work for and with in the past. If you want to get more information about ECC, please go to our website. You have an opportunity to see ECC past projects. You will have a chance to check how you can get access to ECC reliability data. We have a reliability database for rail and process industry, oil and gas. We have a FEMEA database, RCM database, and reliability database. So another important aspect is consultant service. You can check which are the consultant service that we provide. You can look on the product software that we have. You can look on here papers. That's very important information. In papers you can download the papers that we use to put in there. So let's start to describe the one very important concept of reliability. So RAMS means reliability, availability, maintainability, and safety. Availability, we consider operation availability, percentage of time that system is available during a specific period of time. Maintainability is, of course, probability that system has to be maintained, repaired, or replaced during a specific of time. Safe means state of condition that system are operating with a tolerable risk. And of course, we not focus on safety presentation, and let's go to reliability concept. That's the most complex and important one. So reliability is the ability of system product to perform its function without a failure during a specific period of time under predefined operation condition. Robustness is the ability of system to stand still its function without failure when operated under a higher stress level than predefined. And durability is the ability of system to stand still its function without a failure and not degrade its remaining useful life when operate under higher stress level than predefined. So these three aspects is very important when we define and develop whatever products that we have, and that's also applied for infrastructure system. The main question that many infrastructure managers ask is why we need to implement RAMS program for infrastructure systems. So the first one answer is infrastructure system is integrated with other systems and will affect the system performance in case of unavailability or accident. That is the case for energy system, for a nuclear power plant, for example, or even bridges that can degrade and and cause a major accident in case of disruption. So civil infrastructure systems are safety critical by nature and may trigger major accident in case of failure. The case of the example that I just mentioned about the bridge. Communication energy system infrastructure and availability may cause a high impact on our system availability and high loss of cash flow, and also may trigger major accidents. Another aspect is that infrastructure systems are currently vulnerable to climate change and natural disaster, which requires higher level of robustness. So it's quite new, and the new infrastructure system designers need to take into account that in the future these infrastructure system will be vulnerable to climate change and natural disasters. So, and another aspect is that there are many aging infrastructure systems across the globe which pose intrinsic risk of failures that may trigger accidents or have a negative impact on our system availability. So these are the answers why we need to implement a RAMS program. And to implement a ROS program, the first step is to define the reliability strategy, vision, mission, and goals and targets. And after that, we need to have a program. A program has the four pillars. That's our reliability culture, leadership, organization structure, and resource. Human resource, people that work reliability, professional reliability engineers. You need to have investment. These engineers need to have training, need to have software, need to go to conference to get new ideas, and so on. And those are the pillars for RAM programs. If one of these one is missed, the RAMs program is compromised. And then, of course, in addition to RAMs program, to run strategy and RAMs program. When you establish the RAMs program, we'll define all the procedures that are the guidelines for the reliability engineers for implementation. Then, of course, as part of this procedure are the RAMs method that will define the reliability requirement, the RAMs requirement, as well as verify if this requirement can be achieved based on the design configuration, based on the type of system, of course, the past data, the data provided for the vendor suppliers. And then based on it, we start to verify the RAMs performance achievement throughout life cycle, of course, in design phase, but we validate that during operational phase. It's important to understand that such runs methods are applied along life cycle. And then, of course, in the very beginning, we define the strategy of your physical assets. Then you develop this asset strategy and targets throughout different system levels. Then during the design phase, we start to define equipment level of concern runs requirement, and to do that, you need to apply different reliability methods. And then you verify these targets in a lower level, and you also do bottom up and top down. First you start to top down requirement definition, but here you can start to verify your system in high level when you do some bottom analysis and equipment level. And then, of course, during operation, whenever necessary, we implement some of this method, but currently here, what you used to do is follow up your warranty terms based on performance and constantly have your FRACA system, your reliability analysis to verify this performance. Very important aspect is that such reliability methods are always linked in different phases. So the run model that you do in concept phase will go in more detail in system, equipment level, and design phase. So use this model and update it in design phase. In the design phase here, you perform FMEA, that is the input for RCM. And the RCM that maintenance preventive task will be the input for run model. And the run model will be the input for the LCC. And all this run model and LCC will be the base for the warranty definition and will be verified during operational phase. Similarly, we have the FMEA that will be the basis for the FRACAS codification, and then the FRACAS will be during manufacturing or before the operation will be defined, established, should be to follow up the system performance during operational phase. So very important aspect is to understand that all these methods are linked throughout the life cycle phase. So let's take a look on some examples. Basically, we have qualitative and quantitative reliability methods apply for infrastructures. One example of qualitative method is failure modes and effect analysis. Basically, this method identifies the system infrastructure. The subsystem is a bridge. The subsystem have different parts here. So if you get the peer, we have a failure mode. We have a cause of failure modes, and here you can see that we have a consequence, a possible collapse. So that's very high level, and we need to mitigate this risk based on some actions. In this case, we define preventive maintenance action. Then we consider here that if we perform preventive maintenance task inspection, we are able to identify these failure modes and avoid this consequence. And that's what will be the next step. That will be RCM. So we do that for all the bridge parts. So we go through the RCM, and the RCM use the same structure, the same definition that we had the FMEA. And then what basically do here is to define, for example, the example that I focused was the pier crack. And here I have the type of maintenance and when I will perform each type of maintenance and which frequency to identify this failure mode here. So, and then of course I can use this type of tasks here in my run model. So this is the RCM is applied for the whole system and use the FMA as a base. So these are qualitative methods. We also have quantitative methods. So here, one example of one of the most important reliability methods, that is the lifetime data analysis. So basically, what we have different here is that these in usual components and equipment we get time as a parameter. So here we get what we call milligram tons. So milligram tons is applied for assess the stress, the load in a track. So this is an example of rail track. So we consider along the time how is the load in this track. We can have 50 kilometers track, 10 kilometers track, or whatever, but we know the load, and based on the load, whenever we identify some failures, we identify what's the load, and then based on it we can basically implement the good enough fit in the map to define which are the best PDF. Here is viable 2 parameters and or 3 parameters, and here we can define the parameters. So since we define the parameters, we can automatically define the reliability along the time. Then we can see here, for example, that's around 8,000 MGT. We have 100% of reliability in this track. After that, reliability is starting to decrease. Another quantitative method that we can use is what we call probabilistic degradation analysis. This method, the difference that I use the input for preventive maintenance non-destructive tests. That's when I measure the crack in this track. For example, I can have, in this example, I have 5 points of measurement, and I start to measure the crack evolution. I have a limit crack that I consider failure, that is this 10 millimeters, and then of course, whenever measure I do, I have the MGT reference value here. So what I'm going to do now is to plot the trends that each one of these measurement points have to achieve this 10 millimeters. And then I perform good enough fitness test to perform this assessment, and then I'm able to predict the trends for achievement for each one of these 5 points when they will achieve the 10 millimeters. And here I have the MGT time. So for example, if here we have the limit one, and I plot the trend for each one of these 5 measure points. That's represented for different 5 colors. So if I get this example here, this point, that is this one here, if I plot on the x-axis, I will have the MGT value. So if I do the same for the other 4 points, I will have 5 points. With 5 points, what I can do, I can predict my reliability. So basically, I come back to the previous methodology now. With the MGT values, I perform the good enough fitness test, and I will check which are the best PDF that fit on my data, and based on it, I can have my probability density function that shows me that this is the gamma one, that shows me that's the high chance to have a failure, a crack, functional crack in this track between 120 megatons and 8,000 megatons. And then of course, if I have the PDF, I can also plot the reliability. That basically shows me the probability that system has to operate 100% until 8,000 MGT. Another method is of course the run analysis that have reliability block diagrams. Each block represents one system. This high level means my whole infrastructure system will shut down if one of the systems shut down. And then I go deeper in this level, and then of course I'm concept phase. I'm starting to define my requirements, my reliability requirements, operational reliability requirements, the time, the reliability requirements, expected number of failures. Then I can go deeper. So here, for example, is this infrastructure system, and start to define it to lower level. Then, of course, I will perform a simulation. I input all preventive maintenance inspections, reliability, PDFs, data, parameters, and maintainability parameters. And then when I run simulation, the system will start to plot the failures, or if I have preventive maintenance, when the preventive maintenance takes place to avoid the failures. In the end, I have the number of shutdown, and that's how the system calculates the reliability. Another aspect during the design is the safety method that's also applied for infrastructure system. So usually the most common method is the system hazard analysis. The system hazard analysis, basically we have this example here. This one is applied before the construction of the bridge, but we also apply these same methods during the design. So for easier to understand, let's give it this example. So you have different construction phase that you're describing here in this list. Then on the right side you have the system hazard analysis. Basically have the system, that's the infrastructure, the elements, we have the bridges, for example, we have the type of hazards. Then of course you have the phases. That's such tasks are defined as defined here. So, and then of course you have hazard, the causes, the consequence of the causes. So here, for example, if we have lack of structure instability and structure the eruption and collapse, we have the cause of that is lack of geometric measurement and controls, and that can cause a multiple deaths because it's a breach, the eruption of the breach. And then of course this risk is not acceptable. We need to implement some mitigations, and these mitigations will take place in some requirements that need to implement during the constructions. And then by implementing that, we have the risk mitigated. So this is a type of safety analysis. There will be requirements that is implemented for different parts, different involvement organizations. In some cases, my experience, we have some organizations that are responsible for the bridge design, but other organizations are responsible for to build the bridge. So they take all these requirements that define design, they accept this requirement. Then of course the state or the organization that will operate and maintain the bridge will also take other requirements, and that is part of RAM's program. But what happened during operational phase now? Since I perform all this analysis during concept and design phase, manufacturing phase, or construction phase, now I'm operating my physical infrastructure system. Then of course, as I mentioned in the beginning, most or all of system infrastructure systems are safety critical. They are safety critical elements because they can cause a major accident. This major accident is triggered by a combination of this type of failures, integrity failure, or human error, or hardware failures and software failure. Here is included material failure in case of infrastructure. And then to mitigate that, we need asset integrity management. And this asset integrity management is a combination of safety management, risk management, as well as maintenance management. That's including reliability. So we have here preventive maintenance and reliability inspection tasks, and we also need to consider human factor of our teams to avoid that we have this human error that can trigger major accident. And that are the elements that we have in asset integrity management. Another very important aspect that we nowadays are able to incorporate artificial intelligence to measure the performance of our integrity systems, infrastructure system integrity. So basically the idea here, for example, we can use a sensor to measure vibration. This bridge, this plot of vibration, this graph of vibration acceptable level will be compared with the ones that consider failure. So by comparing and classifying the profile of this picture here, that's the sensor that's the vibration captured by sensor, we can classify and define where there will be a failure based on deep learning methods, and then automatically trigger alarm, and then the maintenance team will look on these specific bridges and specific parts. So we need to incorporate artificial intelligence as part of asset integrity. Then one of important aspects is that our asset integrity management, that is the deploy here in this picture and highlighting red, will be part of the whole asset management process. So basically we perform we constantly measure the performance of our assets based on inspection, based on predictive maintenance, based on a prognostic health management, based on reliability. Then whenever we have some failures, degradation, or even failures and degradation and incidents, we put this information in our failure reports. Then we have a summary of anomaly management system. We classify which are the risks for each of these anomaly, and we prioritize actions. And then, of course, in terms of safety, we have a barrier system that's defined that. So barrier system will be able to, for all critical elements, to mitigate and to have a graphical vision what's the impact of the system. Then, of course, as we defined before, we have a list of inspection. This is an example for railway system that we need to perform along the time, and we check and we manage that along the operational phase. And then additionally, it was very important that we will have our let's say prognostic health management, monitoring critical safety elements and the remaining useful life, the states of health, and in addition, we have also the reliability 4.0. That's basically for whenever we have for data in our FRACA system, the system will be able to automatically calculate the reliability index and plot the graphs. That's avoid the calculation, complex calculation, use different software and so on during operational phase, and that's easier for technicians, for operators to understand. To you don't need to calculate the reliability because it's automatically calculated. So let's jump to the conclusion. So RAM's program implementation for infrastructure system requires culture for excellence and high performance achievements. For infrastructure system, whatever other system, this excellence culture to develop reliable, robust, and durable products that have high performance, have no early life failures is very important. Without this culture of excellence, there is no culture of reliability. Reliability and excellence is strongly associated. So this second point is RAM's program implementation for infrastructure is still a huge challenge despite of lack of risk perception, belief that such system will never fail. That was one of points that I strongly face the resistance when I work for here in Europe for a major infrastructure system project. That's the high level organization have this belief that the infrastructure system will never fail or hardly will fail, and because of that we don't need to put the effort investment on RAM's program implementation. Another aspect is that RAM's program implementation starts from strategy definition, vision, mission, goals, and aftermath before RAM's program elements must be constantly supported by high-level leaders and organization. This is essential, otherwise the system is not implemented, and that's why in many cases RAM's program implementation have hard times and are not 100% implemented in many organizations. In addition of that, we need to consider that usually nowadays organizations change their teams, change their leaders, and then it also affects the RAMS program. If the RAMS program is not well established, if the guidelines are not well established and procedures are not well established, and there's not a training material to update it and to training the newcomers. So this is also a very important aspect. An infrastructure system face current change, climate change, and future natural disasters. We face that, which require high robustness and durability. So we need to keep that in mind for new designers. Unfortunately, the old school mindsets in many projects is you need to deliver the fast as possible the project to make cash flow. But unfortunately, if you want to do robust and durable infrastructure system that will face this climate change and future natural disaster, you need to spend more in your designing time, people, and of course in investment. So the bibliography for this presentation is on my book RAMS Analysis Engineer for Rail Industry Analysis Model and Optimization, the second edition that's only electronic available in Amazon. And of course the FIMEA RCM examples for railway industry are available in ECC database as well as for oil and gas process. We have two databases, one for railway and another one for oil and gas. So thanks for the opportunity to present in this conference. If you have some questions, please send me a mail and contact me.